stand here. So, okay. Welcome, everybody. Glad you could make it this evening. Quick question. Is anybody exceptionally warm? And don't look at me, because I just sweat. Okay. Let's see if we can turn it down a little bit. It gets kind of stuffy in here with all these people. This is fantastic. Glad you're here. My name is Andy Sainer, as some of you may know. You're at the Lunar and Planetary Institute here in Houston. And tonight is our, This is our fourth presentation in our current public lecture series, exploring the solar system today and tomorrow. Our final and fifth presentation will be on June 2nd with Dr. Alan Treman from here at LPI, giving us an update on where things are at with the Curiosity rover on Mars. And he's going to talk about the tires, or the wheels, I guess. So if you've been hearing about that, you're gonna hear some more of that at that time. A couple of things you may have seen on here I want to just kind of reiterate. On May 9th, there's a transit of Mercury, which means you'll be able to see Mercury going across the face of the sun slowly, but you can see it. We're going to have a telescope set up at the Freeman Branch Library from 10 to noon that day, as long as it's not cloudy. So you're welcome to come out and see the transit as it's happening. It's kind of a cool little thing to see. Plus, you get to see the sun, which up close. Bring your sunglasses. One of our scientists, David Kring, who you've probably heard speak before, he'll be giving two presentations at the Houston Museum of Natural Science, May 24th and June 30th, as part of their lecture series out there. So if you want to, there's a flyer fed out front if you want to go see that. He's a good presenter too. You got to buy tickets, but that's their thing, not ours. But those should be good talks if you want to go here. One's about lunar exploration. The other one's talking about the threat of asteroid impacts. So a fun one and then a scary one to balance it out. And on the flyer, it says that it'll be in the planetarium, and that's true. If you look at it online, it says it'll be in their big theater. We just found out recently that they're going to do it in the planetarium because they just overhauled the system and got this nice, great new system in there. So they're going to do it there instead. At the end of tonight's presentation, of course, we'll have a Q&A session. You can ask your questions if you have it. If you do, please raise your hand. There'll be two of us going up and down the aisles there with a microphone. That's so, of course, we all can hear it, but we're also recording. We're also streaming live on Ustream, which we did the last presentation. So again, manners. I beg. Oh, and of course, whoa. Let's just do this. There's a reception, of course, following afterwards, chance to chat with our tonight's speaker, Dr. Bagenal. But first, I'm going to sit down and have Dr. Paul Schenk come up. He's one of our scientists you've heard speak about Pluto and Dawn, and he's going to tell us more about tonight's speaker. And then remember to turn the lights down.
Welcome. We're going to talk about Jupiter today, and I'm going to introduce Dr. Fran Bagenal, who I've known since I think Dirt was young, I think. And I asked her over dinner to tell me what she wanted me to tell you about her. And this is it. Grew up in England, came to the U.S. as a graduate student at MIT for a year, but got involved on Voyager, and that was it. Okay. But there's actually a lot more to it than that. She's been involved and correct me if I'm wrong, but I think every spacecraft mission to the outer solar system since Voyager days, which was in the 1980s, I don't think that we've actually missed any of those. And she's been studying the small microscopic particles that get blown off by the sun and sweep through the solar systems, known as the solar wind, and how they interact and populate the magnetic fields of the giant planets. And she's been working on Voyager. She worked on Galileo, which orbited Jupiter, Cassini, which is still orbiting Saturn. And just this past year, New Horizons at Pluto, which has some interesting things that we discovered there as well. And now on Juno. And she's going to tell us about what Juno is going to do at Jupiter. And she's actually complained to me that she helped write a book about Jupiter, which was published in 2004, ironically called Jupiter. And she's now going to have to rewrite that book because of the discoveries of Juno. So I give you Fran Bagenal.
Thank you very much. Okay. Thank you very much indeed. And it's really exciting to have flown past Pluto. Wasn't Pluto cool? The New Horizons stuff? absolutely amazing stuff. To go from Pluto last July to flying past, going into orbit, we hope, around Jupiter on the 4th of July with the Juno mission. So I'm going to tell you about the Juno mission, what we hope to do, and why it's important for solar system exploration, and in fact understanding how the solar system formed, how different solar systems form, maybe around other stars and so on. So let's start off with our usual idea of what the solar system, big planets are involved. Jupiter, Saturn, Uranus and Neptune, two pairs, Jupiter and Saturn, 10 times the size of the Earth, 100 to 300 times the mass, and then Uranus and Neptune are a few times Earth masses, 20 or so Earth masses, and about a few times the size of the Earth. But we're really interested in Jupiter, the biggest one, 300 times the mass of the Earth, and how it forms, it plays a role in the formation of the solar system. It's the big planet of the solar system. So these are pictures that were taken by Voyager and by Cassini, improved cameras over time, and Cassini was able to take a really fantastic view and put together, once we map it out in the latitude and longitude scheme, we can then look at the movie showing the clouds moving back and forth. And you can see the east and west flowing winds, the white ones going one way, the red ones going the other, and of course the Great Red Spot, which has been observed since we first put up telescopes to look at the sky since Galileo's time. We know that the Great Red Spot has been there. So what are we really looking at? Well, what we're looking at is the outermost layers of a planet, and the white clouds, we're seeing reflected sunlight, all colors of the spectrum. And when we're looking at the red ones, we're seeing clouds that tend to absorb in the blue part of the spectrum and reflect red. And we think it's sulfur that's causing most of that reddening of those clouds. We believe there are three layers of clouds: an outermost layer that's ammonia particles that form clouds. The middle one is a mixture of ammonia and sulfur, ammonium hydrosulfide. And the bottom one, we believe, we can't see it, is water deeper down. Now, what are we really looking at? Well, what we're really looking at is a big gas bag. This is a gassy planet. It doesn't have a surface. And what we're looking at is the way things work at the giant planets and a lot of the planets around other stars, is that if you add gas and you add more gas, it's a bit like a stack of pillows. And you keep you've got mass pushing down, so you have more pillows, you've got more mass. So at the bottom, you've got more deeply compressed material and then less compressed up here. So pressure is increasing with depth, just as our atmosphere is down near sea level versus up at the top of Everest. You've got much less pressure at the top of Everest. It's the same sort of thing. And this is really all just gravity pulling down on gas as gravity pulls down on pillows. So if you add more pillows to your pile, what happens is it doesn't increase in height by one pillow's worth. It gets compressed down. And so what we find with the giant planets is that they end up, Jupiter and Saturn being more or less the same size, as are many of the planets around other stars. You're just adding more material and they get more and more dense inside. And so Jupiter is 3 times the mass of Saturn, but it's more or less the same size. There's not a lot of difference in size. Okay, so let's think about the outer layers, what we're seeing. Well, we have the same sort of situation as we have here on Earth. When we have gases rising up, they condense. But because the Jupiter spins every 10 hours, rotation plays a major role. Coriolis force is important. And you end up turning that rising motion into east-west winds. And so we have these belts and zones, as they're called, when you look at the planet. So if you look with a telescope, and I encourage you when you to go out now is a very good time. We have Jupiter high in the sky when it's not cloudy. You can see it clearly, and you can see with a relatively small telescope the belts and zones. Now, if you look with an infrared telescope, you can look at the hotter parts deeper down between the clouds, and the colder parts look black higher up. So it's sort of inverse of what you see in the visible part of the spectrum. What you're seeing in the infrared is the internal glow trying to get out. And this will be an important thing when we start talking about Juno science. Okay, so we have these white ammonia clouds, ammonia hydrosulfide clouds, the yellow ones below. And of course, the great red spot is a big storm system that we've been observing since Voyager time in detail, and seeing it swirling around. It's a high-pressure system in the southern hemisphere. We can take our observations of Cassini taken in the equatorial plane and project them onto the pole, and we see these belts and zones continuing up towards the poles, but we don't have information in the actual polar region. This movie is kind of cool, and it shows you these belts and zones continuing quite a long way up, but we don't really know if they continue to the very polar region because we haven't flown over the poles. Now, we wanted to know what was inside Jupiter, very important for understanding the formation of the solar system, as I said, and we wanted to know what the cloud system was like. So the Galileo mission sent a probe into the atmosphere in 1995, and so what we expected to see with this probe that went in, we're measuring all the weather parameters, was we'd expect to see these 3 layers of clouds as it went in. But what we actually saw was very little, virtually no clouds at all. So what on earth was going on? Well, what was happening was, in fact, that where the probe went in was between, luck would have it, it went between these cloud layers, right? And so when we look at where it went in using the infrared, an infrared telescope, this doesn't seem to have come out very well, but where it went in was actually in a hot zone, which was a downdraft region, where we were between the clouds. Okay, so why do we really care about the clouds of Jupiter? Well, it has to do with understanding how the solar system formed from a big cloud of gas, material condensed out to form the core of the planet, and then gas being entrained into Jupiter. And so what we thought was that when you look at the abundance of elements, the main principal highly abundant elements, we expected that the inert gases, helium, neon, argon, krypton, and xenon, what we see is that they're all enhanced by about a factor of 3 over the sun, over the solar abundance. And so we suggested that that was the sort of abundance of material that was being pulled in to make most of Jupiter. But then when we look at carbon and nitrogen, yeah, it's consistent, sulfur consistent, but we didn't see any water. So if you take oxygen, the 3rd most abundant element in the universe, you'd expect there to be a lot of it in Jupiter. You add oxygen to hydrogen, the most abundant element, you get water, right? So if we don't see water clouds, where is the oxygen? And what's going wrong with our theory of the origin of the solar system? So to keep things simple, astronomers have this periodic table, and hydrogen, helium, and oxygen is number 3. And as I say, if we can't get oxygen right, then we really don't understand how the formation of the solar system works. So this is our idea. We think that as this gas collapsed, it was hot inside close to the star, and the low abundance, let me just go back to that table, you can see the things that make up rocks are very low abundance. And so rocks and iron, we know then that we make small rocky planets in the inner solar system, and we make large giant planets that form outside this snow line, where we think large snowballs accumulated of the material that condensed the water, a bit of ammonia, methane, nitrogen, CO, but mostly water, form these huge snowballs. Once you get a snowball that's about 15, 20 Earth masses, you start pulling in the gases that are there, particularly hydrogen, and you make a big gas giant. Okay, so this is our idea that we've had for many decades now of how the solar system formed. But if we go to Jupiter and find there's no water, or we're lacking water, what on earth is going on? What is wrong with our theory of how gas giants form? So this was a motivation to go back. And you might say, well, let's just send a whole bunch more probes and maybe end up going into the wrong place, in which case you're stuck and you don't really know, did you go to the wrong place or did you just, are our theories wrong? So what we decided to do was to find a new approach. We were going to go and look for water, but not by sending probes in, by sending a spacecraft that gets really close. And I'll show you in a bit how we're going to measure it. So it turns out that there wasn't enough plutonium-238 around to make radioisotope thermoelectric generators. We had to come up with a new way of powering our spacecraft, and we decided to use solar panels, and these are the large solar panels that we have on Juno. And so this is our spacecraft. Here is a human, right, down here at the end of the solar panel. This is a 60-foot diameter, okay, really large solar panels that provide about 200 watts of power out at Jupiter, where, of course, the sun is about 25 times weaker than it is here at the Earth. But that should be enough to power our spacecraft. Our spacecraft has a variety of instruments, a magnetometer at the end of the boom, a couple of energetic particle instruments, JADE and JEDI. We have a wave instrument that will measure plasma and radio waves, a couple of spectrometers, a UV spectrometer, an infrared spectrometer, and we have a microwave instrument that will measure microwaves, and that's going to be very important for measuring water. Gravity science will be using the radio antenna to measure motions of the spacecraft that tells us about the gravity of Jupiter. Oh, and yeah, we've got a little camera. Yeah, we threw that on. It's a PR instrument. So, you know, in the space exploration business, as you probably know, the cameras rule because the public relations and everybody wants to see the pictures of what's going on. And Mars, the rover, getting stuck in the sand. Those of us who measure charged particles and magnetic fields and gravity waves, you know, we have to put up with the spacecraft being pushed around to take all the pictures. And if we're lucky, please, can we make a measurement? Please, can we make a measurement? And the cameras let us make a measurement occasionally. On this spacecraft, we will tell the cameras where they're pointing and what they're going to see. And we will make our measurements. And if they're lucky, they will get a picture to show to the public. I exaggerate, of course. But it will take some really cool things. But it's a spinning spacecraft. And so you can imagine with a spacecraft that is spinning every 30 seconds, you're not going to be able to turn and move and target things very easily. But there will be some choice about what we're going to observe. Okay, we'll come back to the camera later. Okay, in the meantime, in order to make the measurements that we want to make, we have to get very close to the spacecraft. Sorry, we have to get very close to Jupiter, to the planet. And that means we have to go into the radiation environment, which I'll show you in a minute. And so when we built the spacecraft, we put all the electronics, or most of the electronics that we could, inside a vault with a really thick titanium encasing to protect it. Because this is what we are going to have to do. So here's Jupiter, and around it there are very strong radiation belts. These are like the Van Allen belts of the Earth, but more intense, more dangerous. These are 10 MeV electrons, which are very energetic, penetrating charged particles that will, if they go through your electronics or through the skin of a human, for that matter, we're not taking humans here, by the way, but the electronics very easily get damaged by these charged particles. And so we are trying to protect the spacecraft. We've designed our spacecraft, our mission, our orbit, to go over the poles, duck under the radiation belts, above the clouds, and then back out again. And it takes about 2 hours to go from pole to pole. It's moving at 60 kilometers a second. It's really moving fast over here. And then it spends 2 weeks out here sending the data back to the Earth. And then we do it again, and so on. So that's great. Very well-designed trajectory. The only problem is Jupiter spins every 10 hours. So rotation is really important. And so it's actually much fatter at the equator than the poles, about 10%. So this ablateness, this flattening, this equatorial bulge, causes the orbit to go from here in the equator, dipping down. And after 16 orbits, it's dipped down here, and by 30 orbits, it's dipped all the way down. And so you can see, after a dozen, 2 dozen, maybe 3 dozen orbits, we're going to be going right through the middle of this lethal radiation environment. So we don't know how long this spacecraft will survive. If we only get 10 orbits, we'll learn a huge amount about Jupiter. But we're hoping that we will go for 30 or so orbits and survive, but we just don't know. It's a new environment, new world. We just don't know what that will be for our spacecraft. Okay, so that's the plan. And what we're going to do is we're going to map out the planet. We're going to design our orbit so that we scan different regions. We come back at different longitudes and measure the environment around Jupiter at these different longitudes. And we're going to do this in a variety of ways. The first thing we want to do is to measure the distribution of mass inside Jupiter. And to do that, we want to measure the gravity. Now, this is done a lot with various space missions. And there have been missions, say you have a planet that has rock and you have a big mountain here. If you have a spacecraft flying over that mountain, the gravity will be put stronger over the mountain, if you like, pulling the pendulum or pulling on the spacecraft as it goes over the mountain. And so we can map out the gravity as we've done for the Earth in gory detail. Really quite impressive what the GRACE spacecraft has done at the Earth and the GRAIL spacecraft has done on the Moon, measuring the distribution of mass. You can see the impact craters and how this affects the mass on the Moon. Now, the way we're going to do this is as follows. We use the radio antenna that has a transmission back to the Earth, and as the spacecraft goes along, if there's a uniform gravity, the spacecraft is not very much perturbed on its orbit. But if there's a gravity inside that perturbs a detailed structure, it'll make the spacecraft wobble, and there'll be a detectable Doppler shift in the radio signal that's being sent back to the Earth. And so we use this Doppler shift to tell us about the gravity, the distribution of mass inside. And the way we do this in space science is to measure the power as a function, which is a vertical scale here, versus complexity. The higher this number is along here, the greater the degree of complexity. So the low order structure that happens over most of the planet will have a low number. But if there's a small scale structure that happens at one region or another, it'll be at the higher number here. So for Jupiter, we've only measured the very low order, very high power structure. And what we hope to do is to measure, and this red line is just a wishful thinking of a theorist that says that we'll be able to measure the power at very high order, which will give us the complexity, the detailed distribution of mass inside Jupiter, and this will tell us where the mass is and what's going on inside. Okay, so what we think is inside these gas bags, Jupiter and the other giant planets, is we have this idea there might be a core deep inside. We have an idea that we have hydrogen above that and it much denser deeper down. So I'm showing that these figures are being, maybe there's a translation with this projector, but let me talk you through what we're seeing here. The density here is low up high, and compared with water, so this is about the density of water, 1, we get down to a density of rocks and really dense metals deep down inside. And this is because of the gravity pulling down on the gas. And the temperature rises up to about 4 to 5 times the temperature of the surface of the sun. So it's really hot inside because of the high pressure. Now the pressures are very high. In fact, the number that you can't read here is 100 million times the atmosphere of the Earth. So what do these pressures actually mean? Okay, so I'm going to tell you what that means. When we talk about pressure, we're talking about weight or mass being pulled by gravity. And I have a certain weight, more than I should have, but I have a certain weight, and I can feel the force of gravity through my feet. And there's a pressure through my feet. And I can calculate that pressure as my mass times the force of gravity per unit area of my feet. Okay, so what happens to the pressure? Pressure is force per unit area. If I stand on 1 foot, what happens to pressure? Does it go up or down? By a factor of? Right, I've halved the area, and so I've increased double the pressure. Okay, so in order to talk about the pressure of the gas in this room, you have to have 5 people standing on my shoulders above me and all that weight coming through my feet. That is the pressure in this room. You can do the math to check. It doesn't seem credible because we're so used to it, right? We're used to that pressure. But if you were out in space and your spacesuit was evacuated, you would suddenly realize, yeah, you're used to a lot of pressure that is going away. Okay? So that's the pressure in this room. What about the pressure deep down inside Jupiter? What's it like there? Well, we can't use humans. So, how about elephants? Okay, so let's have an elephant. Okay, let's have an elephant standing on 1 foot. Nah, not enough. You need 1,000 elephants standing on top of each other, and the bottom elephant standing on 1 foot on a stiletto heel. And then you begin to get the right sort of pressures, right? Sort of something like 50 to 100 million bars times the pressure in this room. So we don't really know how hydrogen behaves at those pressures. I mean, we can't write a proposal to NSF saying, could I have 1,000 elephants? I want them to stand on each other with the bottom on a side of hill. Even Lawrence Livermore and the places that study hydrogen at high pressure, maybe related to hydrogen bombs, maybe. I mean, I don't know, but I would guess that maybe know about this stuff. They don't get to these pressures, okay? And so we are sort of making it up. We don't really know. We're working on a realm that we do not have experimental evidence. And so we have to rely on theorists that tell us what happens when you take hydrogen to such high pressures. Now, we have taken hydrogen to a couple megabars, a couple million times the pressure in this room. And what we know is that molecular hydrogen, which is 2 protons and 2 electrons, right, in a molecule. What happens is when you get to very high pressure, you break those apart and the protons and the electrons can move around separately. Okay, so once you allow positively charged protons to move around, negatively charged electrons to move around, you can now drive electrical currents through that fluid. Okay? And so we move to, hydrogen turns into what we call a metallic phase, where it becomes electrically conducting. And so in many ways, deep inside Jupiter, we think this transition happens somewhere about 80% of the radius of Jupiter, much deeper down in Saturn because of the lower mass. It turns into something like liquid mercury that you have in your thermometers, right? So a liquid metallic material at fairly high pressures. So this is the story, and this is the cartoon that we started off when we launched Juno. And we thought, well, we'll look inside, and we're going to see a core inside of rock and maybe ice materials with the hydrogen around the outside. But you know what's happened is, the current idea is that in the time since we launched in 2011 and now, the theorists are beginning to say, yes, but when I do my quantum mechanical models, and you know, I nearly put it on a German accent because it turns out the guy who does this is a quantum mechanics guy, is German. And I think a lot of us think of 19th century physics and the early quantum mechanical people having German accents. So I can't help thinking in a German accent when I talk about this. But we have quantum mechanical models of hydrogen at these very high pressures. And we thought originally that, you know, that there would be a core inside of those heavier elements, those bits of iron and nickel and sulfur and so on, oxygen and carbon deep inside. But they're now saying that once you get to these high pressures, you just have metallic hydrogen, and all of the heavier elements become dissolved in that liquid metallic hydrogen, and they will just be sitting around as separate elements, and it would be all mixed up, and you won't have a special core, a distinct core. So this is the sort of picture we're thinking about now. Is it like this, where you have something a bit more like a Easter egg, where you've got multiple layers? Or do you have a more mixed up, I've got to think of the name of the chocolate. There's probably some kind of chocolate that I could describe that looks like this inside. But, you know, is it more mixed up with the heavy elements being mixed up rather than a concentration deep inside? So this is what we're trying to sort out by measuring measuring the gravity field. Will tell us about the distribution of mass inside and maybe the flows inside. That's why we want to measure the gravity. The other thing we want to measure is the magnetic field, because this liquid metallic region will be turning over and we'll have a dynamo. And we expect there to be a strong magnetic field inside. And what we really want to do by flying over and through this environment is to measure the magnetic field of Jupiter. We have some idea about the dynamo structure inside, but we really don't know what the flows are and what are the flows that might be driving it. This is from a model, but it's just the outer layers. What's it really like deeper down? So we're going to do the same sort of thing with the magnetic field as we do with the gravity field, measure the power as a function of complexity or scale. And what's interesting is when we do this with the magnetic field of the Earth, what we see is that we can measure this out to quite high order, something like about 11 or 12. But the problem then is, because the Earth has a crust that can be magnetized, the rocks of the outer layers of the Earth can be magnetized. The most detailed structure that we have at higher order, the higher level of complexity in the magnetic field of the Earth, is all in the rocks, in the outer layers. It's got nothing to do with the internal dynamo. So once we look to higher order structure, we're not learning anything about the dynamo. With Jupiter, because we don't have a crust, we don't have rocks that are magnetized in the outer layer, we hope that we will continue measuring the complexity to quite high order, maybe as high as 20 or so, that will tell us about the dynamo, and we'll perhaps know more about the dynamo of Jupiter than we do about the Earth in terms of degree of complexity inside. We really don't know what it will be like, and depending on the scale of that metallic region, we don't know what the extent is of the dynamo, how far out it goes. So this is what we want to do, measuring. We're going to fly over and get a sense of, is the flow inside sort of cylinders, which is one theory, or is it that the flow inside is in fact more turbulent, more like the sun's dynamo, where everything is turning over in small structures? So we hope to find out what it's really like by measuring the magnetic field and the gravity. Okay, so that's the deep interior. What about the outer layers? What about the water? What are we going to do there? Well, we know in the outer layers we have these layers of cloud. We want to measure the clouds and the distribution of water and ammonia. And we decided that instead of sending more probes, what we would do is to measure the microwaves that come from the inside. Now, you all know that microwaves are absorbed by water. That's how you heat up your cup of tea in the microwave oven, right? You put your water in there, you turn it on, and the water heats up. It's the same sort of thing we think is happening. The deep interior of Jupiter is really hot. It's retained heat of formation, and that heat leaks out, and we want to measure that. We want to measure the amount that's absorbed by the water clouds and the ammonia clouds, and so we're going to measure at 6 different wavelengths of microwaves between 1.3 centimeters and 50 centimeters, so wavelengths sort of in this range, and this will let us get a measure of the distribution of water. So we have these 6 different microwave antennas. The spacecraft's going to be flying over Jupiter, spinning, and as it spins over, as it goes over the planet, we will be able to measure the outcoming radiation in microwave and measure at different wavelengths, and will tell us what the distribution is of water and ammonia, not only as a function of depth, but we also will be flying over in these strips and measuring the distribution relative to the clouds. And so how much what is the distribution of water and ammonia as a function of both height and latitude and longitude. And so this will help us get a sense of how much water is there inside of Jupiter and how is it distributed. Okay, so that's what we're going to do to give us the distribution of water. Now, we chose this orbit to measure the gravity field, the magnetic field, and the microwaves to give us the water and ammonia. But because we happen to be flying over the poles, we're going to be able to fly over a unique region which we have never flown before, and that's the magnetic field region, the magnetosphere of Jupiter. Jupiter's magnetosphere is huge. For comparison, here is the Earth's magnetosphere. The whole magnetosphere would fit within the planet Jupiter. Whereas with the Jovian situation, where the field is much, much stronger, we have a region, this bubble, this magnetic bubble around Jupiter, that extends up to 100 times in the direction towards the sun and extends in a long tail away from the sun all the way out past the orbit of Saturn at 9 AU. So this is a really long tadpole-like thing, large volume. It's dominated by the rotation of Jupiter, and it's filled up with sulfur and oxygen that comes from Io. Now, as Paul Schenk here will, I think, agree, Io is one of the most weirdest and exciting moons that we have in the solar system. It is volcanic, as Voyager found out. It has plumes of sulfur dioxide, spewing out. There are hot regions shown in this infrared image. There's high-resolution region shows there are up to 300 different hot volcanic regions. We look a few months apart with the Galileo cameras, and we see there's a complete area, not quite as big as Texas, but as big as regular states in the United States, like Colorado, that are covered with new lava every few months or so. And so we know that this is a very active region. It's the most volcanic object in our solar system, 100 times more volcanic than the Earth. And so it's very active. All the water has been removed, and the sulfur and oxygen that comes spewing out actually becomes escapes from the planet, becomes ionized and trapped in the magnetic field of Jupiter, and you get this big torus that extends out, in fact, beyond interacting with Europa and Callisto to some extent. But this is a ultraviolet glowing donut of ionized gases that are trapped in the magnetic field. The magnetic field, like the Earth, wobbles with a 10-degree tilt, and so you end up with this wobbling around because of the tilt of the magnetic field. So this ton a second of material that comes from Io fills out this magnetosphere, and it becomes accelerated in the magnetic field. And what happens is those particles eventually come bombarding down onto the atmosphere of Jupiter and produces the aurora. And if we look at Hubble Space Telescope data, and I've just got to show you some of these fantastic data from Hubble, where we have, these are like raw images or semi-raw images, but I think you get to see the dynamic nature of this aurora. You have a fairly static ring of aurora, and then in the center you have these bright spots, which we don't really understand why these are coming and going occasionally. And then we also see, you will see a spot and a path. Let's wait for the right one to happen. And here it comes, coming around. You can see, here it is up here. You can see, here it is down here. And it's a spot. They're actually a series of spots and a wake behind. And these auroras are associated with the moons, Io, Europa, and Ganymede. We've been looking for Callisto, but it's harder to find. And these are electrical currents that are produced in the interaction of the moon with the magnetic field and the trapped plasma. And those currents flow along the magnetic field into Jupiter's atmosphere, where they trigger these auroras and generate this light. And there's a lot of power in that. And these are millions of amps currents that are flowing along the magnetic field into the planet. So this is a very dynamic environment. We're going to be flying with the Juno spacecraft right over this region. And so what we'll be doing is we'll be flying over, we'll be measuring the charged particles that are streaming along the magnetic field, we'll be looking at the aurora, and we'll be trying to understand what is the connection between the particle environment, the magnetic field environment, and the aurora that we're seeing below. We've never flown through this region before. At Jupiter, we have a good sense of what happens at Earth. We can test our ideas of the physics of how this works at Earth and apply it to Jupiter. Is it anything like the same, or is it totally different? So it'll be very important physics experiment, as well as understanding all this energy that gets poured into the upper atmosphere of Jupiter. So that'll be a very dramatic time for us to fly through this region. Okay, time to show you the spacecraft. They actually let me go inside and have a look. I had to dress up like this so that we keep the spacecraft very clean and don't get any human dirt onto the spacecraft. You see, the engineers are all dressed up like that too. Someone stood next to me. I'm not an experimentalist, so they were really watching me very carefully. But I just went in and had my picture taken next to the spacecraft. I couldn't resist it. Okay, so let's look at the time-lapse movie. And they put it all to music, and you look at the time-lapse, and it goes on, and it's great. So the engineers, they put a piece on, they diddle about with it, measure it, take it off again, diddle with it more, bring it back on again, diddle with it, put it back on. I'm trivializing it. This is a lot of work to make this spacecraft work, right? You know, it's a lot of work. And it takes months, in fact, a couple of years to put this together. And, you know, it's a lot of work with a lot of people putting it together. And you realize, yeah, a lot of people have put a lot of time and energy. It's probably about 1,000 people per spacecraft, right? One of these relatively small science spacecraft to put this together. And, you know, they have tea breaks and they go off, but, you know, they're working pretty hard. It's kind of cool. Okay, time for launch. Let's skip ahead a little bit, because that movie goes on quite a long time, even with a time lapse. So the spacecraft's all put together. We put it inside, slap a fairing on, put the stickers on, take it out to the Cape. That's the most important bit, right? You're putting the stickers on. Take it out of the Cape, put it on the top of the Atlas V, and then we roll it out, and we get the team in front, take the pictures. Okay, but Lockheed Martin put 2 cameras on the spacecraft somewhere around here. And so I'm going to show you the launch movie, and what you will see is looking down at Cape Canaveral as it was lifting off. Many of you maybe have seen these before, and you're yawning and thinking, oh, not another one. But I think it's just way cool. And not only that, with the way Lockheed Martin did this, because rockets is a very manly thing, I have to say. Okay, they've got some heavy music here. Start the music, come on. Acts don't like it. Time lapse. It goes a lot slower than this. Took about half a day.
Status check. Go Atlas. Go Centaur.
T-minus 10. 5, 4, 3, 2, 1. Ignition and liftoff of the Atlas V with Juno on a trek to Jupiter. Planetary piece of the puzzle on the beginning of our solar system.
Okay, you're looking down, right? Here's a solid rocket. There's the cake. A lot higher up now, above the clouds. This is the limb.
And we have solids 1, 2, 3, 4, and 5 jettisoned.
Keep the main engine going. Now we have black sky, limb of the Earth.
Current altitude is 45.8 miles. In altitude, downrange distance 69 miles, velocity 5,413 miles per hour. We have retros and stage separation.
They separate the upper stage from the main engine, and then they spin it up, and it's off.
We have ignition and full thrust on the aeroplane. Centaur closed loop steering has been enabled.
Like the good old days, yeah. Yeah. Okay, so here are the specs that he was announcing 3 minutes after launch. I just think this is really impressive. I mean, yes, getting out of Earth orbit just getting it launched is a lot of work, and then the upper stage takes it out of Earth orbit. Okay, so what we did was we left Earth orbit up with the upper stage, got us away from the Earth. But not enough to get all the way to Jupiter. This is a 8-ton spacecraft. We had to come back. We did a deep space maneuver. We came back and flew past Earth, got a gravity assist from the Earth. The date it's going to show was actually wrong, but it was in late 2013. And then we're off. We've got enough energy to climb out now of the sun's gravity field and head off towards Jupiter. And we are now, next Friday, we will be 500 Jupiter radii from Jupiter. We're on approach. We're getting there. So let me just show you the Earth flyby. We actually tested a lot of stuff, including going through safing, which is good that we do it at Earth, not at Jupiter. Recovered. Learned a lot of lessons. We took a lot of pictures. This was a view looking up, and you could see Juno flying by. But the coolest thing was that we got all of these amateur astronomers to send their radio signal up to Juno saying, "Hi, Juno," and Juno measured it and sent it back. So it's kind of cool that we actually communicating with the spacecraft. So this is what we're doing. We're on approach. We're the sun's over here on the right, and so as of today, we're somewhere around here. Okay, and we're on our way to rendezvous with Jupiter. We are going to come in pretty close, and then we'll fire the engines on the 4th of July, and then go into. Or what we're going to do is This is looking from the sun or from the Earth. We'll come into approach. We'll do 2 53-day capture orbits, and that'll give us a chance to do a couple of flybys into that really hazardous environment close to Jupiter, get a feel for it, check that Juno is doing okay, and can survive through that environment. We'll learn how the system works and so on. And then we'll get into we'll do a period reduction maneuver and then go into these close in every 2 weeks. And, we don't know how long we'll last. We hope to last for 30 orbits. But like I said, if we only get 10, we'll learn a huge amount about the interior of Jupiter, magnetic field of Jupiter, the distribution of water, as well as the aurora. The cameras. So we're going to do something really cool. This really is an education public outreach camera. We will hope to do some science. But what we're doing is we're going to put up on this website a bunch of choices of where we're going to take the data and bring the data down with the camera. And people can go and vote on what their preference is. So we will go and look at the targets. If you want to look at the red spot, you want to look at a little brown spot, you want to look at a big cloud that's going by, you want to look whatever you want to look at. But the other thing that's really cool is that there are already hundreds of pictures of Jupiter that have been taken by amateur astronomers that are already up on this website. And we're encouraging people who are interested in doing data processing, a lot of image processing people in the amateur astronomy community. In fact, I'm reluctant to use the word amateur because these people are very proficient and very capable. And it'll be great to combine the observations up close that we take with Juno with the ones that they're taking from Earth observations. And so this will be an exciting new way of doing science and involving the public in the science that we're doing. So we're on our way. We've only got a few months to go. We're really looking forward to understanding what's inside, where the water is. Are our theories of solar system formation have to be thrown out of the window and start all over again? Or is there the amount of water that we think there's there? What is the distribution of material like inside? Are the quantum mechanical guys right in that there's heavy elements are dissolved in the hydrogen and spread out? Or do we have a distinct core as shown by this cartoon? Thank you very much. Okay, I'm happy to take the questions. Somebody's going to run around with the microphone, is that right? Okay, what about this woman here in the red? Hang on a second. You wait for the microphone. Yeah.
Thank you for your presentation. Is this on?
Yep.
So the orbit goes around and it precesses into the deeper part. How many orbits before it precesses back out into the slot?
Oh, excellent. Excellent. So I showed you this idea that if Jupiter's here and we go fast over the poles and then it goes out here, and that this orbit begins to precess like this. Indeed, as you're guessing, it will in fact come around and come out the other side. Well, it's about 1 degree per orbit. And so 90 orbits to go vertical, 180 to come out the other side. So chances of surviving that are pretty slim. The other problem is we only have money for 36 orbits. So first we have to survive, then we have to ask for money. But we are planning to go at the end, into an orbit that would eventually degrade. So what we do is we bring down the closest approach a little bit so that after some time, and we're thinking thousands of years, it will eventually go into Jupiter because it must not hit Europa. Right? We all know why. Because we were told all these ones except for Europa. Yeah. Except no landings. Well, right. So the thing, of course, is that we did look into the planetary protection, and the speed that Juno is moving at, if it did hit Europa, it would basically vaporize. So I'm not too worried. It's not carrying plutonium, so it wouldn't sink through the ice. So the chance, it's pretty unlikely that we will hit Europa or anything will happen. It's an extremely low probability. But yes, there's a question over here. Do you want to? Who's got where's the? Oh, maybe I can do this. Here, let me give that to you. There we go.
Thank you for the great presentation. I'm not sure this is on, but I'll speak very loud. Thank you for the
Okay.
great presentation. You alluded to the idea that Jupiter formed in the outer solar system, but if I understand correctly, the niche theory would imply that it propelled itself out there. Is there something you can determine from the data that will support or refute the niche theory?
Okay, I'll repeat that question. So, the picture I showed of the solar system formation with that big disk and the snow line and Jupiter forming beyond the snow line and so on was the sort of a few decades ago, and things have evolved in our ideas of solar system formation. And there's still the idea that Jupiter and Saturn, the next part of it was to say Jupiter and Saturn form where they are, more or less where they are, but Uranus and Neptune formed in close and then got kicked out. And I think that's now gaining a lot of strength, and maybe that new planet X that's been discovered by the Caltech guys could indeed be a third Neptune that was sort of Uranus and Neptune that was kicked out. So the most recent theory, called the Grand Tack, says, what if Jupiter formed probably where it is now, but it had an excursion going inwards and then went further out again? And I don't fully understand. I've heard one or two presentations on this. The question is, would we be able to tell from just looking at the interior of Jupiter? I don't think that we can take the thousands of computer models that people have done and say it's this one, not that one or that one, right? But what we will be able to do is to say this class is clearly not going to work, and this class has a hope of working from looking at the distribution of water. At least that's my expectation. Could be completely wrong. If we don't find any water and there's no oxygen inside Jupiter, then, I really don't know where we go. But, I mean, getting some sense of that number will constrain it. Also getting, I think, some of the other elements will be important, because it's not as simple as that original picture. People are now talking about pulling in different parts of the periodic table in different ways. And I think we'll have a much better knowledge after, but I doubt we'll pin down, it'll be the last word in solar system formation. But it's all getting very interesting. It's not as simple as we thought it was, a few decades ago. Another question. Okay. You're going to give this man a microphone?
No. I'll just talk.
I can repeat it.
Not a lot of people are aware that we're actually going to try something very similar at Saturn soon.
Oh, yes.
And maybe you could describe a little bit what's going to happen in the next, starting late this year.
Right. So Saturn, as many of you know, has had a spacecraft called Cassini that's been in orbit around Saturn since 2004. Did I get that date right? And so it's a long time now. I mean, that's 12 years now. And in the next 2 years, they've changed the orbit of Cassini so that it will fly similarly over the poles again and through close to the equator. I think it's going to go, perilously close to that ring plane or those rings. At least at Jupiter, we don't have to worry too much about the rings, the ring plane region. And we'll do similar measurements of the deep interior with the gravity measurements, the magnetic field measurements, as well as flying through the polar regions of the aurora. And so it's going to be extremely valuable to compare these two giant planets, one that's 100 Earth masses, Saturn, and one that's 320 Earth masses, Jupiter, and see what the relative comparison is about their interiors. We do know that their interiors are different, but how different they are is going to be very interesting, and make these comparisons. So comparative planetology is always the game of planetary science, and it's going to be great that we're going to have these two happening in the same epoch. So yeah, it's next couple of years are going to be really interesting for giant planets. Okay,
just quickly, since you only have funding for 30 orbits, but our electronics do marvelous things, are you going to try to get funding for the 181st orbit to see if it just might wake up again?
Let's first get into orbit. JOI. We'll do it one step at a time. This young woman here had a hand up too. So let's. Yeah.
I'm Louise. I'm author of The Speed of Light. And what's the latest thinking on why Jupiter gives off so much radiation that's so much more than receives from the sun?
Okay.
And how can it keep spinning so fast after billions of years?
Right. So we have to be careful when we use the word radiation. When all of what I've been talking about so far has been about particles, protons, electrons, ionized sulfur and oxygen that's trapped in the magnetic field. But I also mentioned the fact that it's hot inside and it's radiating out, and that radiation is in the form of photons. And I was talking about microwave photons coming from the interior and infrared photons coming from the interior. And so that is the heat that comes from the interior. And in fact, Jupiter radiates 2.5 times the amount of energy that it gets from the sun out in the form of heat. And so it's hot inside. And the main reason why it's hot inside is because of the heat of formation. You take 320 masses of the Earth masses and you pull that all together. That's a huge amount of gravitational potential energy that you convert into heat. And it takes a long time to cool off. The way I describe this to my astronomy students is it's a bit like Jupiter being a big fat baked potato and the Earth being a pea. And it's about the right scale in terms of size. But of course, what you're interested in is the volume to surface area ratio. And that really scales with the size. So when it's big, it retains all its heat, remains hot for a long time, like a big fat baked potato. And so Jupiter, which is the big fat baked potato, of course, retains all its heat inside. It gains extra heat when it forms and keeps it for a lot longer. And so it's really just heat of formation, as well as a little bit of radioactivity and differentiation and so on. But it's mostly the fact that it's big that means it radiates a lot in the form of heat. Yes. Yeah. You can do fairly straightforward calculations for doing that. And it's just left over from formation. I mean, there's still some heat of differentiation and radioactivity, but that's mild compared with formation. Why is it spinning? Well, when it collapsed, it conserved angular momentum and kept spinning. And it has a lot of spin momentum. There's not a lot to slow it down. It's not interacting with other objects. It's hard for other objects that are not anything like as massive as it to have torques on it. So there is a little bit of interactions, gravity between the moons and Jupiter that is slowing it down a little bit. But it's pretty slow. It's got a lot of angular momentum in that spinning big 320 Earth masses. Yeah. Yeah. Oh, nope. Far away. You. Good. Yes.
Since Juno and the recent missions of Pluto and Cassini and how NASA's been lately been impossible to especially the Martians last year, do you think there's going to be another space age, especially with SpaceX coming?
I hope so. I've given dozens of public talks related to Pluto, and the enthusiasm is huge. I mean, I think it's just certainly cool what we're finding. I thought it was going to be really kind of boring, to be really honest with you. And then I look at the surface, particularly the geology, and I'm going, who ordered that? It's just really mind-boggling what we're finding and seeing. And I think people really are inspired and excited. And what I would like to see is that we send robots. We can get into the robot versus non-robotic some other time. But I think what we should do is send robots off all over the solar system and then bring all the data back and then give every kid gloves and goggles so they can go and explore our universe, our solar system, using the data from those robots all over space. I think it would be fantastic. Let's just send hundreds and hundreds of small sats all over the solar system and find out what's out there. I think it'd be great. And I think there's some enthusiasm for that. And missions are getting cheaper. Actually, we're learning to do things more affordably. So the Juno mission and the New Horizons missions are part of the New Frontiers line, which are about $1 billion per. So over 10 years, that's a cafe latte per taxpayer. It's cheaper than the popcorn you paid for when you went to see The Martian. Let's not go there. I'm going to let you do the control of the questions.
Kind of following up on that question, after Juno does bow out to radiation after hopefully 30 orbits, the outer solar system kind of will be going dark for a while. So maybe talk about, are you concerned about the future of planetary science with kind of the scarcity of missions to the outer planets after Juno?
I think that we will go to Europa. That's the next one on the docket. I think we'll do that. We've come up with good plans of how to do that in a viable way. It's a difficult mission. But I think we all want to know what is underneath that ice, what that brown gunk is. Is it whale poop? We want to know what's there. And I think we can do a viable mission that is affordable. That's somewhere between Juno and Cassini, maybe geometric mean of those two. We can do it in an affordable way. I think that we have huge capability of doing these things with robots that are amazing. So I'm not so pessimistic. I think, yes, if you look at the dates, it takes a long time to get to the outer solar system. You've got to be patient. But I think we'll be at Europa before too long. We'll go to other places. So I want to ask you, you saw the Pluto pictures, which are absolutely amazing, right? Now, but do you think we should go to Pluto again, or should we go to Eris or Makemake or Haumea? What do you think? Should we go to the other Kuiper Belt objects? Or do you think we should go to Pluto again? What do you think? Asteroid belt? Yeah, we're going to the asteroid belt. We've got lots of missions going to the asteroid belt. Uranus and Neptune. Absolutely. Okay, so we're going to learn about the giant planets with Cassini and with Juno. But what about Uranus and Neptune? Those are very interesting. Those things that have a lot of water inside them. We know there's water and ammonia and methane in those. They do not have metallic hydrogen inside. They do have magnetic fields, so they seem to have ocean dynamos. It's a really strange different environment. What about those moons? What about Triton? There's a whole business of people now thinking about, well, if Triton is a captured Kuiper Belt object and it looks so different from Pluto, what happened to Triton that didn't happen to Pluto? So there's going to be a whole bunch of papers, people looking at those. Maybe Paul's going to write half of them. But we'll find out what's going on. So yeah, absolutely. I totally agree. I think there's plenty of places we want to go. And we'll go there. We'll go there. Any other questions? Or I'll let you need to the man with the microphone.
Yeah. A real quick question about the metallic hydrogen in the center of Jupiter. It's in a magnetic environment with the sun. Is that a potential dynamo that's actually generating? It's a superconductor.
Right.
So is that a dynamo that may be producing energy actually?
Well, what's happening is that the internal heat is turning it over, and you've got rotation of the spin, and those are the ingredients that you need to make a magnetic field. And we know Jupiter has a very strong magnetic field. So it's a magnetic dynamo that's generated in the metallic hydrogen. In the same way the Earth's dynamo is in the liquid metallic iron that's deep in the outer core of the Earth, which has internal heat turning it over with a bit of spin, and you make a magnetic field. Now, I know we need those three ingredients. Actually making it work is a lot harder, and our dynamo models are fairly crude right now. But certainly it seems to be if you have those three ingredients, you do make a magnetic field. And the details we will learn. Now, I put this up here because I thought someone would want to know about the Great Red Spot.
Yeah, nobody cares.
Do you want to know about the red spot? It's getting smaller. Isn't this cool? So if you look at the top left, that was the Voyager data. It was about 20 2 degrees of longitude, so that's about 3 times the size of the Earth, and it's been getting smaller. These are Hubble Space Telescope pictures and Galileo pictures. It's getting smaller, and if we project further, what we see is at the time of Juno, it should be somewhere around, I think it's about 12 to 14 degrees in size, so half what it was at the time of Voyager. And maybe by 2050, it will disappear. Or do you think it'll come back? What do you think? Go away? I mean, we've known it's been there since the 1600s. How can it disappear in our lifetime? We don't. Well, it must have been back then. It must have been comparable to the Voyager size, if not bigger. Yeah, yeah.
We'll take one more question.
Tossing that one out.
To a layperson, it would seem that using the process you explained, that the mass distribution or gravitational distribution would look the same to Juno, whether there is a rocky core, very small, or a point source, if you will, versus distributed matter throughout. How can you tell the difference?
Well, you can. You look at those. It's not spherically symmetric, partly because of the oblateness. Okay, so you're breaking some of the symmetry there. But also, we think that the inside there's actually cylinders, right? So then you've got flowing around the outside, which causes, and the higher the structure, it's not clear how uniform it is, right? And then the question of, I don't know how well we're going to determine the actual detailed variation in density with radius deep down inside. I think we will be able to tell if there's a distinct discontinuity, a sharp boundary between the core. It's really hard when you've got that large amount of mass. The core is only, 15, 20 Earth masses when you've got a 320 Earth mass object. So it's a little hard to get it super accurately. But I think we'll do enough constraints on the density and distribution to constrain that pretty well. The big question here is knowing the equation of state, the relationship between density, temperature, and pressure, and that depends on the material, on our understanding the material. And so I think the physicists will have to work with the data and we'll iterate on this with those quantum mechanical models, and our gentlemen with the German accents will help us sort this out. And it's science is an iterative process. We won't solve it all in one go, despite what we wrote in the original proposal from NASA. Truth be told.
Let's thank Dr. Bagenal one more time.
Okay.